Hello, we are representing Group 3, Section B, and our topic for today is detecting fake news using machine learning. Today, we are diving into a very relevant and high impact use case, which is detecting fake news using machine learning. With misinformation spreading faster than ever, building models that can distinguish between real and fake news is more important than ever. In this video, we will review how we built a fake news detection pipeline using KNIME. And we'll also cover everything from data loading and cleaning to feature extraction with TF-IDF and finally training models with Naive decision trees, and XGBoost. Let's get started. So we'll start with our step one, which is load and combine data. So our first step here is loading the dataset. I'm using the fake and real news dataset from Kaggle. It contains two separate CSVs, one for real news and one for fake. I used the CSV reader node twice to load both the files. Then added column to each using the constant value column node. This column labels the articles as either real or fake. Then using the concatenate node, I merged the two datasets into one. Next, with the column combiner, I merged the headline and body text into a single column. And then I used row ID to set a unique identifier, and finally the rule engine to define a target label column in string format. Now we have one clean data set ready for the next step, which is the text processing. So before we extract any feature, we need to clean and standardize the text, which is the general uh, logic we need to do as part of any machine learning. I converted the combined text column into documents using the string to document node. Then came the typical pre-processing step, which is punctuation erasure to remove the symbols. The next, case converter to convert the text into lowercase. Stop word filter to eliminate the common filter words like the, and, is, etc. And then the snowball stemmer to reduce words to their root form. So number filter was used to actually look at like whether there are numbers in those text, and document viewer gives you a general output of what the document looks like. So with text pre-processing, this exercise helps reduce noise and dimensionality for our models later. Moving on to the next step, which is feature extraction with bag of words and TF-IDF. Now it's time to convert the clean documents into numerical features. First, I use the bag of words creator to tokenize the text into terms. Next, I use the TF-IDF nodes to calculate the term frequency and inverse document frequency respectively. Then I used a manual math formula here to multiply the TF and IDF manually. Instead of, since we were not able to get a TF IDF node within uh, 9, this manual logic was applied here. So what this does, it gives us a weighted feature vector that highlights important distinctive terms in each article. Now, why are we doing this TF IDF? Because it helps highlight words that are unique to a document instead of just frequent words. So here is how the output looks like for the bag of words. Uh, we will hold on for a second for it to load. Yes. So basically, it's actually using the document text or the NLP document here and then extracting the term from these. So initially, we had 2000 rows for real data, 2000 rows for fake data. So combining it, our total input was 4000 rows. And then with bag of words creator, the 4000 rows is converted into almost 5.68 lakh rows, which is basically using each row of those 4000 and tagging it to the specific words that has been extracted. Okay, so now moving into step 4, which is document vectorization and partitioning. So the output of this TF-IDF needs to be converted into a model-friendly format. For that, the document vector node is used. So the document vector node actually converts this into a matrix format wherein all the rows is then like the 4,000 rows is then mapped into the bag of words in a column format. For example, these are the list of columns that we have created from the bag of words, and the TF IDF value has been assigned to each of those 4,000 rows based on the number of words it has identified. Then I ran the domain calculator to ensure the label column is correctly treated as nominal. So the output of a document vector sometimes doesn't treat the R label as nominal, rather it was considered a string. So we had to convert it into nominal, and this node was used. And then finally, I split the data into the partitioning node. So I used 70-30 split here. So 70 for the testing data and 30 for the, sorry, 70 for the training data and 30 for the testing data. So if you look at here, I have used a joiner node. This is specifically because the output of the document vector do not have our label and the row ID column specified. It only has the columns and the document text. Basically, the mapping of the IDF into the bag of words to each of those document rows. So from the output we have from rule engine, I created a column filter to filter out the row ID and the label, and then use that in the joiner node. And the output of the vector node is also connected to the joiner, which will actually combine or merge both these data before sending it to domain calculator. So this will help me retain the label, which is our unique target variable. Okay, so moving on to step 5, which is our last and final step, which is model training and evaluation. So with our data ready, I moved to the model training using 3 different algorithms. In fact, I wanted to try like 5 different algorithms, starting with logistic regression, but due to the enormity of the data, as well as due to limitation in processing of the data, the logistic regression unfortunately was not running. It was giving a Java heap size error, hence we had to exclude it. Then we moved on to naive Bayes learner, and then decision tree learner. In between, we tried random forest as well, which was again not working as we expected due to the volume of the data and the processing power, which was not available for us during this exercise. So we'll stick on to these 3 models for now: naive Bayes, decision tree, and gradient boosted trees, which is XGBoost. So for the model, so each model was trained using a respective learner node that then applied on the test using the predictor node. I evaluated the performance using this scorer node, and this is what we observed for each of these models. So starting with naive Bayes, the overall scorer showed an accuracy of 50%, which is not great, and this is likely due to strong assumptions it makes about the features independence. Then we use the similar nodes for decision learner, and the output for the decision tree predictor comes out much better than the naive Bayes, and our accuracy has bumped up to 55%, which is comparatively better than naive Bayes. And then finally, we tried the XGBoost tree on some XG gradient boosted trees, which is XGBoost. And similarly, we use the learner and the predictor here. And this is how the output looks. So the scorer gives me the confusion matrix with accuracy of around 62%, which is which has increased very well compared to what we saw with naive Bayes. So there are ways we could fine tune it. So Yeah, in between we also used random forest as I mentioned. It was not working, hence we were not able to predict the result accurately. While this isn't perfect, like 61% even though isn't perfect, it shows the right pre-processing and model choice that can make a big difference. So we can definitely improve on this by further using hyperparameter tuning, ensemble models, or by including NLP embeddings like word2vec or BERT. And that brings us to the end of our fake news detection workflow. So what we built today is more than just a data science exercise. It's a small but meaningful step toward addressing a critical issue in today's digital world, which is misinformation. While our models achieved modest accuracy with XGBoost leading at 62%, this workflow lays a solid foundation. There's a plenty of room to build on it with more advanced text features, better models, or even deep learning techniques. And the best part here is we did all this using KNIME's no-code interface, which is making everyone who has no coding background experience, it's making it easy without any concerns. Like it's ready to use, drag and drop. We are having the results right at our fingertips. One call out towards the end that I wanted to make, the data that we have used here contains 2000 rows for each of the CSVs. The actual data set which we sourced from Kaggle had 20,000 rows for each of them. But using those actual data set, the algorithm was not running or the model was not executing perfectly in KNIME. It was taking like hours and hours to execute. So we had to trim down our data. So the data was actually trimmed down in a random way. So we picked from those 20,000, we picked random 2,000 data for each of these. And and the result is for that. So if we would have used like probably the entire data set, our results could have been much better. So that's why we say this model is moving in the right direction, and hence we can explore it further with our entire data set. Okay, that's where we end. Thanks for watching.